So we are going to talk about example 6. So this is example 6 on my screen. The graph that we're going to sketch is a function of x cubed minus 4x x power 4 minus 4x cubed plus 10. So in order to sketch the graph of the functions, we have to follow the following steps: A, B, C, D, E, F. But here, for the function to be sketched, it is a polynomial. So for a polynomial, we don't have an slanted or horizontal or vertical asymptote. So the part D of the graph is basically not in the current picture. So we are going to show how to do A, B, C, and then we will have to stitch all the points together in part E. Then you put everything together, you have a graph to be sketched. So the first part of the graph is to identify the extremums of the function of f to occur. So in order to do that, you have to first find out the critical point and then check whether this critical point is a local maximum or local minimum. So it's actually quite simple. So you have a functions which is x cubed x power 4 minus 4x 3 power 3 plus 10. So in order to identify the local maximum or minimum, you just have to first find the first derivative and then the second derivative. So the idea here is to try to use the second derivative test to identify the local extremum. So we will first set off the f prime to be 0. So by setting this to 0, we are going to obtain the critical points for the functions, and it could be quite easily seen that f primes expressed to be 4x squared times x minus 3. Then the critical point happen at x equals to 0 or at x equals to 3. So we have two critical points. We call it CP1 and CP2. So CP1 is the point of 0, 10. CP2 is the values of the point at x equals to 3 and minus 17. So the values of 10 is obtained by putting f into the function here, and the values of minus 17 is obtained by putting the values of 3 into the function. So these two are the critical point, CP1 and CP2. Now once you have identified the critical point, the next thing you want to do is to find out whether this critical point is a local maximum or local minimum by using the second derivative test. So let us look at CP2 first, because this will be shown to be a local minimum. So you take the derivative of the functions, and then you take the derivative again, you get the second derivative of the function, which is just 12x times x minus 2. Right, so then you check on the sign of the functions f prime prime at x equals to 3 for CP2, and you find that numbers of the derivative at x equals to 3 is a positive number. Therefore, you come to the conclusion that CP2 is an local maximum, so using the second derivative test. However, for CP1, the values of x is 0, but when you put in values of 0 into the second derivative, f prime prime, you find that f prime prime is 0. So in this case, you cannot determine whether the point CP1 is a local extremum or not. You just cannot. So you have to use a different way to determine the point CP1, whether it's local maximum or local. But later on, we will show that that point is not a local extremum. Okay. In order to find out what the critical point 1 is, we have to apply the first derivative test to CP1. So for example, we need to find out what is the sign of the first derivative on the left and on the right of the CP1. F prime is 4x squared times 4 by x minus 3. So x squared is always a positive number. So only the factor of x minus 3 will determine the sign of f prime. But in this case, x is on less than minus 3. So whether it's x less than 0 or x lying on the right hand side of 0 but less than 3, both sides of x equals to 0 f prime will still be a negative. Therefore, there's no change in the sign of f prime. So if you use the first derivative test, that would mean that the CP1 is neither a local maximum or local minimum. It just says the left hand side has is decreasing because f prime is negative, and the right hand side of CP1 is also decreasing. So I use this green color arrow to show that the functions on the left of x equals 0 is a decreasing function for the simple fact that f prime in this region is negative. On the right hand side of x equals to 0, the function is also decreasing, indicated by this arrow to show that the function f prime, the function f is decreasing for the very simple reason that f prime is 0. So, if you look at the CP1, then you come to the conclusion that by analyzing the sign of f prime, then the function is decreasing on the left and decreasing on the right. Okay, and this is not a local maximum nor a local minimum. Then CP2 is identified to be a local minimum. Therefore, the functions must have a shape that looks like this. That is, on the left hand side, the functions is decreasing until it hits the CP2. Then after CP2, the function goes up because the function CP2 by definition is a local maximum. Therefore, on the right hand side, the function is going up, indicated by this blue arrow, which is going up. For the simple fact also, because for the simple fact that f prime when x is larger than 3 is positive. So x larger than 3, this factor will always be positive. Therefore, f prime is always positive in this region. So you divide this f prime into 3 regions. So in this region, f prime is negative. This f prime is also negative. Therefore, the function is both decreasing in region here and in this region. In the region where x is larger than 3, then the function is decreasing. That finish up our bit on locating the critical point, the trend of the function on the left and right of the critical point. So that is the first part of this instruction. So you first identify the extrema of f and the intervals in which f is decreasing or increasing. So A and B have been done. Then we go to the third part. So the third part is an independent part where you are supposed to identify the regions of the functions where it is concave up or concave down. So try not to mix up B and C because people get them to mix up part B and part C easily. These are two different things. To locate the part B interval where f prime is positive negative, you set f prime to 0. For part C, what you do is you look at the sign of f prime prime instead of looking at the sign of f. Right? So this is what I do for the part B. So part B, find where the graph of f is concave up and where it is concave down. Now, how you do that is actually quite simple. You just have to got the expression for f prime prime. Right? F prime prime is equal to 12x times x minus 2. Right? So then you have to identify the region where the f prime has a positive sign, the region where f prime prime has an opposite sign. So how do you locate that? It's quite easy. Then you look at these regions. So when you set x equals to 0, x equals to 2, f prime prime will become 0. So x equals to 0 is the point where the f prime prime becomes 0. So you locate these 2 points, x equals to 0 and x equals to 2, and you look at the sign of f prime prime on the left of x equals to 0 and see whether it is positive or negative. Then you look at the right hand side of x equals to 0 and determine the sign of f prime prime. Then you also do this for the region when x is larger than 2, check the sign of f prime prime. So checking the sign of f prime prime, then you'll be able to tell the concavity. Right? So the concavity of the functions f is divided into 3 regions. In region x less than 0, x between 0 and 2, and the region where x is larger than 2. So f prime is a product of 2 factors, 12x, and the other factor is x minus 2. So by looking at this factor, it's very easy to identify that, say, if x is negative, right? So if x is negative, then 12x is a number which is negative, and a number of x which is negative minus 2 is also negative. So you have a negative factor 12x times a negative factor of x minus 2. Therefore, the regions here f prime is simply a positive number. Therefore, you conclude that for x less than 0, the function has a positive concavity. The positive concavity should have a shape that looks like this. It's concave up, a bowl that is facing up. Then for x larger than 2, this factor is positive and 12x is also positive. So the product of 12x and x minus 2 both where both of this has a positive sign. So it is quite obvious that f prime is just simply equal to positive by referring to the functions of f prime. X larger than 2, this factor x minus 2 times the factor of 12x will be both positive. Therefore, f prime again is positive, but x is larger than 2. So you identify this region to have a concavity up when x is larger than 2. And for f prime between 0 and 2, so for x which is between 0 and 2, the factor of 12x is always positive. But since x is less than 2 but larger than 1 and larger than 0, then this factor is negative. So you have a negative factor times a positive factor. Therefore, f prime between 0 and 2 is always negative, indicating that the graph, the functions between 0 and 2 has a negative concavity or concave arc, which is a bowl which is facing downwards. Okay, so then you have these three regions where you have already identified. You have identified the regions where the functions is concave up, concave down, or concave up. So before we leave these slides, then you should look at the point x equals to 0. When x equals to 0, the left-hand side has a positive concavity, right-hand side of x has a negative concavity. So you conclude that when x crosses 0 from left to right, the concavity changes sign. So by definitions, when the concavity changes sign, it means it is a what is it? It is a inflection point. Right? It's the inflection point. So is x equals to 2, the concavity changes sign from negative to positive. Therefore, x equals to 2 is also an inflection point. So you have established the regions of concavity by analyzing the sign of f prime prime. So it is actually quite simple. Once you have the functions of f prime prime, then you can easily identify the regions where f prime prime is positive, f prime prime is negative. That would tell you the concavity of the functions. Then what you do is that you have to, in order to plot the graph of the functions, x cubed minus 4x3 plus x10, you have to combine the information that you obtain from A, B, and C into a single graph. So B tells you the critical points and the trend of the functions. C tells you the concavity of the functions, and then you have to combine them together. Then in this case, the functions has no slanted asymptotes. I think it doesn't have an horizontal or vertical asymptote. The function just goes to infinity when x goes to plus minus infinity. Okay, so for this particular polynomial, there's no asymptote. So you can get A, B, and C, combine them to obtain the sketch of the function. So what I do here is that I combine the informations from the concavity and the information from the trend of the functions together into a single graph. So the green color shape here is the informations about the decreasing or increasing of function in these three regions. And then this graph, which is sort of like a grayish panel, contain information of the concavity of the graph. So here the regions is divided into three, separated by x equals to 0 and x equals to 3. These are the three regions where the functions has different trend, decreasing, decreasing, decreasing. Whereas for this graph, which is the graph that tells you the identity of the concavity, is divided into three regions as well, but the regions are separated by x equals to 0
and x equals to 2 instead of separated by x equals to 3. Now, x equals to 3 separate the regions based on the sign of derivative, whereas x equals to 2 separate the regions based on the sign of f prime prime, right? So these are the concavity. So what you have to do, you have to work out the trend in region 1, the trend in this region, and the trend in this region, and the trend in this. So basically there are 4 regions. In each region, the functions will be either up or down, and the concavity will be either up or down. Then you have to combine the concavity of the functions in this region and also the trend of the function, whether it's decreasing or decreasing. Then you sketch a graph. So let us look at a very simple example for the regions where x equals to x is in the negative sign. So when x equals to negative sign, the concavity is up. Then the function is known to be decreasing. Therefore, this function has to be a function that is decreasing, and it has to have a positive concavity. Right? So the graph that is decreasing and have a positive concavity would look like this. So this is actually the shape of a bow on this side. Right? So this part of the graph shows a concavity function which is up but decreasing. Therefore, you take this part of the graph and pan it to the point 0, 1. That would be a graph that has a positive concavity but is decreasing. So is the right hand side of the region. So let's look at the next region. The region in the next we have to consider is from 0 to 2, right? But not from 0 to 3, from 0 to 2. So from 0 to 2, the function has a concavity which is down. It has downwards concavity. So the function has to have a shape of a bow that is opposite. And at the same time, also we know the function is decreasing within the region of 0 to 3. And 0 to 3 is larger than the region between 0 to 2. So therefore, from 0 to 2, the function must be still decreasing, but it has to have a positive, it has a downwards concavity. Therefore, from this point to this point, which is 2 minus 16, it is a decreasing function, and the function has to have a shape of a downwards concavity. So from this point to this point, you draw a graph, which is basically a concave downwards graph, which is on this part of the function, right? So this part represents a concavity which is negative but decreasing. Okay, so you just take the right hand side part, then you just join up this part and this part. Then you have a function which is going down, decreasing due to this segment, and f prime prime negative, therefore is negative concavity. Okay, now things get a little bit complicated between the region of x equals to 2 and x equals to 3. So between x equals to 2 and x equals to 3, which is this region, the functions has a positive concavity, right? So the region when x is larger than 2, f prime prime is positive. Therefore, from here to here, the graph has a positive concavity. But between 2 to 3, the function is still decreasing. Okay, you can see it here, the function is still decreasing from 2 to 3. So in the region of x equals to 2 and x equals to 3, the function is decreasing, but the concavity is actually going up. Therefore, from this point 2 to 3, the function is going down, but it has a positive concavity, right? So the positive concavity graph looks something like this, which is part of the bow that is going down, but it is a bow that is facing up. Right? So here you draw the point from here to here with a function which is going down, but it has a positive concavity. So positive concavity is like this part. Right? Then when x is larger than 3, the function is going up according to f prime prime is positive in the region x larger than 3. At the same time, also x larger than 3, the functions has a positive concavity. So when x larger than 3, you have a function which is going up and it has a positive concavity. So you have these 4 regions: function going down, positive concavity; from 2 to 3, function going down, negative concavity; from here 2 to 3, the function is going down but positive concavity. X larger than 3 has a function which is going up and has a positive concavity. So you join up all the trends in these 4 regions, but all these graphs must be continuous and go through these 3 points at the critical point 0 and 3, and also this is the so-called the inflection point. Right? So you have to have all these points labeled correctly, then you join them up. Then finally you get the shape of a function which is like this. So we have this region number 1, and then from here to here is the second region. From this point to this point is the third region, between 2 to 3. And when 3 is larger than 4, then we have this graph. So basically, this graph and this graph are the same. It's just that this graph has a correction, but it's not drawn to the scale. Here, the graph is drawn to scale, so it's quite great. But it doesn't really matter, as I mentioned earlier on. The exact shape is not really matter, but you don't need to draw the graph to the scale, but you have to indicate correctly the trend and the concavity of the graph. So that is how you would sketch the graph correctly. You label the inflection point, you label the local minimum, and you label also the critical point. I think this is also a critical point. This is the inflection point. So this is a local maximum, which is also a critical point. This is also a critical point, and also an inflection point, and also a point which is not local extremum, but the point where the slope is just simply equals to 0. So that finished up the examples on 3 of sketching a graph for a polynomial, right? So of course you can use a Mathematica to plot this graph. Just type in the formula and then let x run from -10 to 10, then you get the graph nicely. But you still have to know how to sketch the shape of the graph by applying the information taken from f prime and f prime to show that you understand that the shape of a functions contains the information of the trend as well as the concavity. And the information of this concavity and the trend of a functions are very important when you apply the functions to obtain some calculations for the physics example. Okay, so knowing how to plot the graph is not important. It's not really that matter, because you can always plot the graph using Mathematica. But knowing how to analyze the shape and the trend concavity of the function by using f prime and f prime is more important. Okay, so that illustrates the example of how we do that. Then we go to the next bit, the example of plotting a polynomial function. This is actually much more complicated than the polynomial. Polynomial, you have no denominator, but here you have a denominator functions, which is x squared plus 1. Then for this particular case also, you would also have an asymptote, right? So this is complicated than the previous example of a single polynomial, in the sense that you have to include also the behaviors of the asymptote. But that's all. It's not that as much complicated. So what you do is that first, again, you would have to find out the critical points of the functions. Then you identify the local maximum, local minimum by applying either the first derivative test or second derivative test. Then you mark the location of this critical point or the local maximum, divide it into the regions that is separated by these critical points. Then you identify the regions where the function is increasing or decreasing based on the sign of the f prime for this function. Then you move on to the next bit, that is to identify the regions which is separated by different concavity. So what you do is that you solve f prime equals 0. Then from there you can identify the regions where the concavity changes sign or not changes sign, right? Then third bit is, by looking at the function, you identify the asymptote, right? So the asymptote could be easily identified by looking at this function. So for example, when you set x equals to infinity, right? So when x equals to infinity, then the functions would maybe we have to look at the asymptote more carefully later on. I think this is a situations where the polynomials upstairs has the same degree as downstairs. So you have, this is x squared plus 2x plus x, downstairs is x squared plus 1. So you have to divide the polynomial upstairs by polynomial downstairs. So in that case, what you remember, if you have a polynomial where the order upstairs and downstairs is the same, then you have to perform a what we call long divisions. After you have performed the long divisions, then you will have come up with a linear part and also a part which is equals to 1 plus function of x in the downstairs. So that function of 1 of the downstairs would give you an asymptote, and then the derivative, no, not asymptote. The part which is the linear part from the long division would then give you the slanted asymptote. So this is the case where you expect a slanted asymptote to exist. Then you have to draw out the slanted asymptote. Then you combine the information from part A, part B, part C, and the slanted asymptote. Then you have to sketch the graph. So the graph can be sketched by following through this procedure. First, identify the critical point. So this is what I do. I don't write it down. If I write it down in a whiteboard, it will become very lengthy. Okay, so first of all, you set f prime equals to 0 because the function is already given to you. It's a complicated function of x plus 1 squared minus x squared plus 1. So you just expand the functions, then you obtain f prime. So it is a length calculations. So you have to know how to perform the derivative of that function. It turns out to be a lengthy one, so I don't do it here. So you can take out a piece of paper and do some sketching. Then within like 30 seconds, so you'll be able to obtain this expression. So after you have obtained these expressions, then you would like to set the f prime to 0 to obtain the critical point. So there's no critical point where the function of f prime is not defined, because the downstairs function could never be 0, right? Because you are adding 1 to x squared. So x squared could never be less than 0. Therefore, it's not possible for 1 plus x squared to become 0. Not possible. Therefore, you have only critical point where f prime equals to 0. And this happens when both x and y, when x is equal to both plus 1 and negative 1. So then you check out the sign of f prime prime at x equals to minus 1 and at x equals to 1. So you check it, you put this into the expressions of f prime prime. F prime prime has a complicated expression. I don't know what it is, I forgot already, but you can easily do this. I should have written it down, the f prime prime. So what you do is just take out these functions and then you perform f prime again to obtain f prime prime. It could be a complicated function, but you still have to do it. So I have done it, but I didn't really work it out in detail. So either you work it out in details or you use Mathematica to tell you what the functions of f prime prime is. So anyway, after you have obtained the values of the function of f prime prime and slot in the values of x minus 1, you will find that f prime prime to be a positive number. Right? So it will be a positive number when x is equal to minus 1. And when slot in x equals to minus 1, then the values of the function at minus 1 is 0. Okay, so since f prime prime is positive, therefore this critical point of minus 1 and 0 is a local minimum. So likewise, when x equals to 1, f prime prime should give you a number which is negative. What number it is, that is not very important, but the importance is that the sign is negative. So then you decide that the values of this critical point of 1, 2, where 2 is obtained by slotting in x equals to 1 into the function's expressions, then this would be then a local maximum. So you have identified a local maximum and local minimum at minus 1 and 1 respectively. So you would then separate the regions of the functions into 3 parts, separated each of it by x equals to minus 1 and x equals to 1. So for x less than minus 1, the functions is decreasing because f prime on the left hand side of minus 1 is negative. Now, how do you see it? Let me say it again. After you have obtained the critical point and identify that these critical points are a local maximum and local minimum, then you proceed to separate the functions into region of x minus 1, x between minus 1 and 1, and x equals to 1. Then you decide the sign of f prime in this region, and this region. Now, how do you decide the sign of f prime? Is very easy. We look at the expression for f prime. Here you have the expressions, and you're looking at a region where x is negative, is less than minus 1. So x squared minus 1, if x is a number which is less than 1, less than minus 1, then this is a number which should be larger than 1. X squared will be a number larger than 1 if x is less than minus 1. Therefore, x squared minus 1 will be a factor which is positive. Right? So 1 plus x squared again will still be always positive. So this factor will always be positive, and this factor will always be positive, but you have negative here. Therefore, f prime in this region must be then a negative sign, must be negative. So this is the conclusion that you could easily arrive at by looking at the behaviors of the function f prime when x is less than 1. So people sometimes get they got confused and they do not know how do you know that f prime is negative when x is negative less than -1. So just look at the contributions of the terms to the sign in f prime. Right? So here again, x squared minus 1 will always contribute to a sign which is positive, because x squared will always be larger than 1 when x is less than -1. For example, if x is say -2, then this will be -2 squared or -1.5 squared. It will be always larger than 1. Therefore, this factor of x squared minus 1 will always be positive, and this is always be positive. Therefore, f prime will always be negative because of the combinations of this factor -1, positive factor, you got a negative factors in the f prime. Therefore, you decide that, then you conclude that f less than -1, the function is decreasing for x less than 1. So you can also look at the region where x is larger than 1. So when x is larger than 1, it's the same thing, right? So when x is larger than 1, x squared will be a number which is larger than 1. Say for example 1.5, 1.2 square, 1.5 square, 2 square is always a factor larger than 1. So x squared minus 1 will be a positive. Then this number is, as I said, always positive in the downstairs. So f prime will always be negative when x is larger than 1. Therefore, when x is larger than 1, the function is decreasing. Right? So this is a function which is decreasing. But then between -1 and 1, then what happens is that when x is between -1 and 1, x squared will be a number which is less than 1. Right? So x squared will be less than 1 if x is between -1 and 1. For example, x would be say 0.5, -0.2, -0.5, or 1 or 0.07. Right? So then this x squared will be less than 1. So a number which is less than 1 minus 1 will be negative, and this is always positive downstairs. So you have a negative factor, and when we multiply together, f prime will always be positive. Therefore, f prime is concluded to be positive within the region of -1 and 1. Therefore, fx is increasing. So you have the factors. You have decided then what is the trend of the function. The functions here will be going down from left to right. Then these functions will be going up, and then this function will be going down. Right? So this is the intervals where the functions is decreasing. So that is the first bit of the questions. Then you go to the next bit. The next bit is to determine the derivative, the concavity of the function. So this is the expressions of f prime prime. So you have to do it for yourself. It's going to be quite complicated. The function, if you differentiate once, you got f prime to be like this. You differentiate f prime again, then you get f prime prime. So this is the function that looks like this. This is very complicated, but it's not really that complicated. You just have to carry out the calculations for the f prime prime. And once you have done that, f prime prime gives you this number, these expressions, then you just have to find out the regions where the x changes sign. So in order to find the region where x changes sign, you have to first find the values of x where f prime prime function sets to 0. So when you set f prime prime to 0, you find that there appears to be 3 values of x where the f prime prime would be 0, namely when x equals to 0. When x equals to 0, f prime prime is 0. When x squared minus 3 becomes 0, then f prime prime is also 0. So the solution for x squared minus 3, 0 is just a values of x equals to plus or minus square root of 3. So you have 3 values of x where f prime prime becomes 0. So you separate the regions of the function into 4. Each of these is separated by the values of x where f prime becomes 0. Right, so I just draw this line to represent x equals to -3, this line represents x0, this line represents x equals to -3. Then again, it could be very easily to check the sign of f prime prime on left or right of x equals to square root of -3. You can easily check also the sign of f prime prime on the left or right for x equals to 0, and the sign of f prime prime on the left and right of x equals to square root of 3. So by checking the sign of the functions, the left and right of these 3 points, you'll be able to tell the concavity of the functions. Okay, so for example, you look at this f prime prime. When x is less than square root of 3. So when x is less than square root of 3, now we look at this downstairs function. The downstairs function is 1 plus x squared. So the function always positive. Downstairs function always positive. So the factor that affects the sign of f prime prime would then be only contributed by 4x and x squared minus 3. So if number of x is less than square root of 3, then x squared would be a number which is larger than 3, right? So for x less than square root, then for the value of x less than negative square root of 3, x squared would be larger than 3. Therefore, this is a positive number. So x squared minus 3 would be a positive number, but x would be a negative number because x is taken to be square root minus square root of 3. So this will be a negative factor. For x will be a negative factor, x squared minus 3 will be a positive factor. So f prime prime would then be negative in this region. That's why I write this as a negative. Therefore, you conclude that when x is less than square root of 3, f prime has a downwards concavity. Then maybe you want to look at the other end of the spectrum when x is larger than square root of 3. So we leave this region and this region to be analyzed later. So this is easier to analyze. X larger than square root of 3, but x larger than square root of 3, x squared is larger than 3, therefore this factor is positive. 4x will be positive as well because x is a positive number larger than square root of 3. So down upstairs you have positive factor, you have also positive factor, therefore f prime prime is positive, that is this part. Then f is a function which has a upwards concavity. Then look at this region where x is between 0 and square root of 3. So when x is between 0 and square root of 3, then what is this? So this would be a factor x squared. X squared, if x is less than square root of 3, then x squared would be then less than a number of 3. So this factor would then be negative in this region. So you have a negative factor, you have a positive factor. Here, x is a positive number between 0 and square root of 3. So you have a positive factor, negative factor, therefore f prime prime is negative, right? So this region has f prime prime negative. Therefore, you conclude that the f functions between 0 and square root of 3 has a downwards concavity. So same thing can be said about here. The concavity is up because f prime prime is positive. So you have to look at the expression of this function and then decide for yourself what is the sign. Once you have decided the sign of the f prime prime by checking the values of x in each of this region, then you will be able to tell what is the concavity of the function within these 4 regions. So you have this region 1, 2, 3, 4, concavity change from down, up, down, up. Therefore, these 3 points are all inflection point because at this point, the functions it changes sign in its concavity. So we conclude that these 3 are the 3 inflection points plus sign change, and we combine this with this. This is an inflection. This is the critical point. So this is a critical point. This is a critical point, and in this critical point, the functions changes its trend, and then this is a point which is a minimum. This is a maximum, right? So we have identified the critical points, the local maximum and minimum by looking at f prime. Then here we have identified the inflection points and the concavity of the functions by looking at the f prime prime. So that finish up the ABC part. Then you go to the next bit. So these functions you can just carry out for yourself. You find that when x goes to infinity, either it's going to positive or negative infinity, then the function will tend to 1. So I leave you to decide for yourself that indeed the function has an horizontal asymptote, which is happening at x equals to 1, right? So when x goes to positive infinity, negative infinity, the functions will tend to 1. So you combine the conclusions or the trend from this part and this part, you put everything together, then you would come to this this slide. So this slide is to conclude the trend that I have analyzed for you. So first of all, I have this region 1, this black color graph, which is sorry. First of all, let us look at the purple color one. For this purple color, you have region 1, region 2, region 3, which is separated by looking at the values of the f prime, right? So f prime is positive, is negative here, f prime is positive here, f prime is negative here. Therefore, I know that this is 3 regions, region from here to here, from negative infinity to x equals to -1, from x equals to -1 to x equals to 1, and from x equals to 1 to positive infinity. So these 3 regions functions is decreasing, increasing, decreasing. Okay, so you have this borderline, which is marked by the critical point, which is also a local minimum, and also at this point a local maximum, which is the critical point. Right. So this is the information that is obtained from f prime. Then the black color information here is taken from the f prime prime. Right. So from the analysis of the concavity, we have three inflection point here, inflection point here, and inflection point here. So I have this black color line to separate the concavity into this region from -infinity to x equals to square root of -3. Then the second regions for the concavity is from x equals to -3 to this, the inflection point 2, which is from -square root of 3 to x equals to 0. So from here to here, the function has positive concavity. Then from this inflection point 2 to inflection point 3, the function has an downwards concavity. Right? So this is again the same information that I already explained to you in the previous slides when we analyzed the trend, when we analyzed the sign of f prime prime. So again, when x is equals to a number square root of 3 larger than square root of 3, then in this region onwards, the concavity is up because the f prime is positive. At the same time, also we have a horizontal asymptote where x equals to 1. So with this information put in together, then it will be possible for you to start sketching the shape of the function. So I would like to graph these functions using my iPad. At the graph on these slides, you can actually see that we are almost there to sketch the graph. So how do you start sketching the graph? So first of all, you have to understand the graph is supposed to be more or less, it should be continuous. So let us start from somewhere. Okay, so let us start from, I would like to start it from the IF3. Okay, so look at IF3 and let's see how we sketch the graph of IF3. So in IF3, it is a region where the functions has a positive concavity. And at the same time also, the functions is supposed to be also, let me see, is supposed to be also decreasing in this region. So you look at this expression here, the function is decreasing. I can't show it here for some reasons. Maybe I make this smaller. Okay, so according to the screen, the functions for x, which is in the right hand side of square root of 3, this function is actually decreasing and it has a positive concavity. So these regions of x has a shape of a function which is going down and it is concave up. So a function that is going down and is concave up looks like what? It looks like something like this. So it's a function that is going down, decreasing, and it has a positive concavity. So these functions has to join to the inflection point 3. So you start off with inflection 3, and then you have a function that looks like this. To make it looks better, let me zoom in a little bit with my iPad. Then I have a function that is coming out from IF3 and is coming down with a positive concavity. And since it has a asymptote at the end, then the function will just go down and it tends toward the asymptote at y equals to 1. So that is the shape of the graph for x larger than square root of 3. So then we can then proceed backwards to find out what is the shape of the graph. The shape of the graph that is lying between the region of x equals to 1 and x equals to square root of 3. So which is this region? So let us try to figure out what is this region looks like. In this region, the shape of the graph is that it has a downwards concavity, and at the same time also it has also a function that is decreasing, and the function must connect the point of the maximum 1, 2 to the inflection point of IF3. So we are now going to draw a line connecting the point of maximum 1, 2 and IF3, where the function is decreasing and it has a downwards concavity. So such a function that is decreasing and have a downwards concavity joining up the maximum point 1, 2 and inflection point 3 would be like this. Right. So this is the functions that is coming out from the maximum 1, 2 going down, and it has an concavity negative. Okay, so to draw this in a more cleaner manner, try this. Okay, okay, so it looks like this. It would be again it come up from here and then coming down, and it has a positive, it has a negative concavity. So this is the graph in the region of x larger than 1 but less than the square root of 3. So that finished up the shape of the region, the shape of the graph in this region. Then we move next to a regions which is in between this point, the inflection point 2, x equals to 0 and x equals to 1. So within this region, the graph will still have an downwards concavity, and the function is increasing, right? So within this region, you have a function that is increasing due to this part, or that the function is increasing, but its concavity is a downwards concavity, which is from here. So we have to then draw a line to connect the IF point, the point IF2, and the maximum point at 1, 2 between these 2 points, which has a function which is increasing but has a downwards concavity. So the graph that is showing a increasing functions and a positive concavity and have a negative concavity will be a function that looks like this. So this is a graph that is a negative concavity but is increasing. Okay, so that finishes up the part of the function that is like that between x equals to 0 and x equals to 1. So this part of the graph has been drawn. Then we move. Okay, I just accidentally so this should be like this. So then the next bit of the questions is to go to the question, the regions between the IF2 and x equals to 1. So which is this region? In this region, x is larger than -1 but is less than 0. So in these regions, we expect the function, it is said that the function is increasing and the functions has an concavity which is up, right? So this is a region that is to be joined up by the minimum point of -1 and the inflection point 2. Okay, so now we are going to draw a graph, a line joining the minimum at -1 to IF2 for a function which is increasing but has a upwards concavity. So how do you do that? So the graph that would appear would be a graph that is increasing but have an upwards concavity. The upwards concavity graph would be like this. This is upwards concavity that joins the local minimum of -1, 0 to IF2. So that is for the regions between x equals to -1 and x equals to 0. So then we move on to the next bit, which is the region, the narrow region lying between x equals to minus square root of 3 and x equals to -1, which is this region. Okay, so within this region, the concavity is up, but the functions has an derivative negative, which is a function which is going down, right? So here in this region, we have to join up the IF1 and the local minimum here with a function which is decreasing, but the concavity is a upwards concavity. So how do you draw a line joining IF1 and the minimum at -1, 0 is very easy. It's a function that has a concavity that is up. So the function that is concavity up but going down would be like this, going down, and it has a positive concavity. Okay, so that is the shape of the function. Maybe I draw this to look cleaner a little bit. Okay, so it's a graph that's going down and it has a positive concavity. Okay, so that is how it looks like, a graph that is decreasing but has a positive concavity. So we are done on this region between x equals to -3, minus square root of 3, and x equals to -1. Okay, so then we are now prepared to move to the next region, which is a region of x that is less than the square root of -3. So within this region, the function is decreasing and it has a downwards concavity, and the function must be coming in from the left and joined with the inflection point 1. So how do you draw a function to the left of the inflection point 1 where it has a downwards concavity and it is decreasing? So a downwards concavity graph would be a graph that is downwards. A downwards function that would be downwards would be like this. It's a function that has a negative concavity. So this is how a graph which has a negative concavity looks like and is decreasing. At the same time, we also know the functions has a horizontal asymptote at x equals to 1. So this bit where when x tends to negative infinity, the function tends towards the horizontal asymptote of -1. So that's how you stitch up all the sections of the graph in each sections by considering the concavity of the graph and the trend of the graph, whether it is increasing or decreasing. So that is how the shape of the graph looks like. Then the answer for these questions would then be easily let me come up from here. So this is a shape that I obtained. But if you look at the solutions, I think the solution for this is, let me see if I can come up from the graph. Okay, I think it is like this. The previous graph looks like this. So the correct answer would be like this, which is just exactly as what we are expecting the graph would be like this. So this is the exact solutions. That is like the graph is moving towards in the negative directions. The graph is going to the asymptote, and then it just goes down and then goes like this, goes up. So this is exactly the shape that I just drawn on the slides. So by having known the values of these informations of this one, the trend of the functions and the concavity of the function in different regions, you just have to then work out the shape of the graph step by step using the method that I just showed you. So if I give you a function and ask you to sketch the graph, then this is a procedure that you can follow, right? So find the critical point, divide the function into the regions according to the critical point, then you find out the inflection points, then divide the functions according to the inflection points, then you decide the concavity within each regions, then you put everything together, join them up, and then consider the behavior of the asymptote, then you'll be able to produce the shape of the graph. Okay, this is a kind of favorite question in exam. If we have exam, then usually you will be given this kind of functions for you to sketch the graph. So that is all for this part of the lecture. Okay, thank you for your reading.